Hello friends. So in the last lecture that we have just completed about the eutectic reactions as well as the partial eutectic reactions. So basically those reactions were very useful for the iron carbon diagram. So just to understand the different kind of that phases in the iron carbon diagram. So those basic part is the very important. So before just going for this particular lecture, you just refer those previous two lectures also. So you can be able to understand what is the different kind of that phases are present in the Fe3C diagram, that is the iron carbon diagram. So we will just, before going for the iron carbon diagram, we will just try to understand what are the different kind of the phases in the iron as well as in the steels. So I hope you will just enjoy this particular lecture, and this is very useful just to understand what is the Fe3C diagram. So again, the examination is concerned, definitely there will be a question on the Fe3C diagram, as well as when you just go for the metallurgical basic concepts, you should understand the FAFE3 diagram very thoroughly, because this is just we can be able to say that is the FEFE3C diagram is the pillar of metallurgy. So in the equilibrium diagrams, many more contents that we have covered, what is the cooling curves and all those things. Now the main content of this particular equilibrium diagram topic is the FEFE3C. So before going for that FEFE3C diagram, you just try to understand what are the different kind of the basic concepts in the FEFE3C diagram, that is the iron and carbon. Now basically in an almost pure form of iron, that is the ignot or wrought iron. So iron has a limited application like roofing, ducts, drainage, culverters, and a base enamel in the refrigerator cabinets, that is stores, also the washing machines, etc. So these are the some sort of the different applications of the iron. So which is very limited applications are there, that is the roofing, ducts, then drainage culverters, then base enamels in the refrigerator cabin, then in the stores, in the washing machine. So these are the variety of the applications of the iron. So an alloyed form, the carbon is mixed with the iron to form an alloy. So basically when we want to form some alloy, we are mixing the carbon in the iron. So we can be able to just go with the some sort of that alloy. So alloy of the iron carbon system are known as the ferrous alloys. So whatever will be the alloy is developed with the help of iron and carbon. So all those alloys are called, or it is known as the ferrous alloys. So they includes the plain carbon steels, alloy steels, and cast iron. So you just try to understand whatever may be the steel. So in the next slide again we will just focus on the steel, because don't be just get the confusion in the steel and iron. So basically the steel, it is just alloy of iron and carbon, and iron it is just sometimes present in the pure form also, that is called as a wrought iron. So basically the percentage of carbon when it is varying, we just go with the different kind of that form of the materials. So basically I would like to mention here the carbon percentage basically varying from 0.08, or we can say 0% to maximum up to 6.67%. Okay, so just the iron, cast iron. So iron basically when it will be in the pure form, it is called as a wrought iron. Okay, when it will be in the pure form, either ingot or wrought iron, it is called as a wrought iron. So basically famous word is the wrought iron. So when that percentage will be reached in between 2.1 to 6.67, that particular iron is called as a cast iron. Okay, so don't be gets confusion. Wi or wrought iron, when the percentage of carbon is below 0.08, that is the pure form of iron, basically it is known as, so that will be a wrought iron. Okay, then when the percentage of carbon present in between 2.1 to 6.67, it is called as a cast iron. Okay, and when the percentage will be go above 6.67, it will be known as a pig iron. Okay, so these are the basically three terms of the iron. Just try to understand it, what I want to say. Three kind of that iron phases are there, and in between that, which kind of that phase, that will be again we will see. So when the percentage of carbon is below 0.08%, means from 0 to 0.08%, that is basically the very pure iron. So that pure iron is called as a wrought iron. Okay, when the percentage in between 2.1 to 6.67, that particular iron is called as a cast iron. And when the percentage will be go above the 6.67% carbon, that particular iron is called as a pig iron. So these are the three phases of the ions. Okay, now when the percentage of carbon in the ion, when it will be in between 0.08 to 2.1%, it is known as the PCS, that is the plain carbon steel or carbon steel. Okay, plain carbon steel or carbon steel. So steel, now this is not called as a plain carbon iron. Okay, it is called as a plain carbon steel. And when we have added some another content in it with the same percentage, like chromium, okay, or molybdenum, just to enhance the properties, okay, or sometimes that nickel elements, when we want to increase some sort of that rusting properties, okay, of iron, okay, that corrosion resistance and all. So we are adding some sort of that elements in it, and when we are adding the element, it is called as an alloy steel. Okay, so what about the steel? In the next slide, we will just go with that particular things. The metal ion is a primary constituent of some of the most important engineering alloys, and hence it is important to study the ion carbon diagram. So basically the metal ions, it is just a primary constituent of most of the engineering alloys. Okay, so that's why it is very essential to just learn the ion carbon diagram. So ion carbon diagram is also known as ion carbon phase diagram, or ion carbon equilibrium diagram, or iron iron carbide diagram. Okay, that is Fe 3C diagram. So these are the different names for the ion carbon diagram. Might be in the examination, it may be the question that just explain the iron carbon phase diagram or iron carbon equilibrium diagram. Don't be gets confused. Okay, everything will be same. That is iron carbon diagram, iron carbon phase diagram, iron carbon equilibrium diagram, iron iron carbide diagram, or Fe3C diagram. So everything will be same. Now we will just go with the steel. What is the steel? Okay, so steels are the alloy of iron and carbon, in which the carbon contains in between the 0.008 and 2%. So which is very important, my dear friends, to understand this. The steels are the alloy of iron and carbon. So basically the steels are, it is just one kind of that alloy. Steel, it is one kind of that alloy in which along with the iron, the carbon is present, and the carbon is present in between 0.08 to 2%. So commercially steel always contain some amount of other elements. So if these elements accidentally present without any intention, they are called as impurities. So basically the steel, if there are many more contents are present, so if these contents are accidentally present in the steel, that is basically known as an impurities, and if they added purposefully, they are called alloying elements. So when those contents are added purposefully, now why we are adding the content purposefully? Just I will want to give the example that chromium, nickel. So these kind of that contents we can be able to add, and it is added just because to enhance the properties of steel. Now, which kind of the property will be gets enhanced by adding those? That is the corrosion resistance. Basically, we are knowing that. So for the surgical applications, means in the medical application, when the doctor want to go with the some sort of a surgery, the basic whatever may be the requirement of those equipments, that is not the strength. So strength, it is not much important, but the most important property, that is the corrosion resistance. So all those equipments, that is the needle or anything, any kind of that some sort of the scissors, so they should have the very high amount of corrosion resistance, so it should not be get corrode. And just to enhance such kind of the properties, the elements will be gets added in it, and those elements, if it is added purposefully, that is called as an alloying elements. So sulfur and phosphorus are common impurities which comes from the coke and ore. Basically the sulfur and phosphorus will be definitely present in the steel because it is just a common impurities and which comes from the coke and ore. Okay, so still with other elements in a small amount are called as a plain carbon steel. So whatever may be the plain carbon steel, it is there. When the steel with some sort of the other elements are there in it, it is called as a plain carbon steel. Now these are the two phases, that is the polymorphism and allotrophy. So polymorphism is a physical phenomena where a material may have more than one crystal structure. That is, the crystal structure may change with change in the temperature or external pressure, or might be due to both. Okay. So just to understand this polymorphism, what is the polymorphism? It is the physical phenomena where the material may have more than one crystal structure. So when the material will contain the two, three kind of the crystal structures, so that crystal structure may change with a change in a temperature or external pressure. So that is called as a polymorphism. And if the changes in a structure is reversible, okay, means 1 to 2 again 2 to 1, okay, so likewise that is the reversible. So if the changes in a structure is reversible, then polymorphic changes is known as allotrophy. So this is the terms of polymorphism and allotropy. Just when we want to go with the some sort of that another contents, you should have the clear understanding of these two terms. Now one familiar example is found in a carbon graphite is the stable polymer at ambient condition, whereas diamond is formed at extremely high pressure. So the best example, known example for allotropy is iron. So for the polymorphism, so carbon graphite is the stable polymer at ambient condition, whereas diamond is formed at extremely high pressure. So for the allotrophy, the best example is iron for the allotrophy. So when iron crystallizes at 1539 degrees Celsius, it is in the BCC structure. Okay, that is the delta iron. At 1404 degrees Celsius, the structure changes to FCC. Okay, so BCC means body centered cubic structure. FCC in the sense face centered cubic structure. That is the alpha ion or austenite. And again at 910 degree, it again comes to the BCC, that is alpha ion or ferrite. Alpha ferrite or alpha ion, it is known as. So delta ion or delta ferrite. Okay, then gamma ion or austenite. So these are the three basic terms. So again, these terms will be explained in the FeFe3C diagram thoroughly. So with the next content, we will just go with the FeFe3C diagram, so you can be able to understood what is the importance of FeFe3C diagram. So I hope you have understood this polymorphism and allotrophy. Now This is the Fe3C diagram. So here we will describe this particular diagram. Okay, so for this particular diagram, we need to explain everything. Again, we have to conduct the one more lecture for this. But here, we will first of all discuss how to draw the FE3C diagram. Now, again, we will see one video just to draw for the FE3C diagram, which is very much important. But don't bother when you are watching this kind of the structure immediately. You might have, oh, what has been written over here. But one by one, we will just go with this each and every content so you can be able to understand. So I will just want to highlight some sort of that portions in this FAF3C diagram. So don't worry about it. It is very simple to understand the FAF3C diagram. And once you can be able to understand, you can be able to say it is the very simplest part just to draw the FAF3C diagram, and then you can be able to explain each and every term, and it is very easy to understand the each and every term. So this particular diagram, we will just go with the some sort of the divisions. So basically, already in the earlier slides, I have explained the steel is having the 0 to 2% of the carbon. So when the percentage of carbon is present from 0 to 2, okay, so here slightly that percentage will be increased, that is 2.06% of carbon. It has been mentioned over here, that is 2.06% of the carbon. So when the in carbon is present, okay, in the iron with the some sort of that contained, so basically up to 2.06% of carbon, it is known as a steel. So again, I want to repeat, for wrought iron almost 0 to 0.008, then in between that again up to 2.1% it will be a steel, again from 2.1 to 6.67% of carbon it is the cast iron, and above the 6.67% of carbon it is just a pig iron. So here on the x-axis you have to draw plot all the percentage of carbon over here on the x-axis, and the y-axis, very important, that is the temperatures. So this temperature will be gets varied on the y-axis. So first of all, when we want to draw or go with this FAF3C diagram, first of all we have to set this two axes. So on the axis 1 we have to vary the percentage of carbon, and on the axis y we have to vary the temperature. So this is x-axis, we have to vary the carbon percentage, and on the y-axis we have to vary the temperatures. So here now this will be up to 2%, it will be a steel, and above the 2% up to 6.67% it is the cast iron. Then we have to plot the temperature on the y-axis: 200, 400, 600, 800, 1000, 1200, 1400, and finally 1600. So basically for the FAF3C diagram, the melting temperature, the maximum temperature will be 1536 or maximum up to 1539 degrees Celsius. So we have to set the last point is 1600. Now here first of all we will discuss about some sort of that contents. So here many more things has been written in this FAF3C diagram. So here you can be able to observe in this particular curve it has been written alpha ferrite, okay, and in this particular line here it has been written alpha plus Fe3C. So Fe3C in the sense carbide, oh sorry, cementite. So this will be a cementite phase. Now this particular diagram, above this 1.39 everything will be in the liquid phase, and below the liquid phase the different kind of that phases has been shown in the FAF3C diagram. So when you will go above this particular temperature, that is 1539, everything will be present in the liquid state only. So there is no any different kind of that phases above the 1.39 degree Celsius temperature. Now, when this particular temperature is dropping down up to 0 degree Celsius, this particular diagram has been divided into the many more parts. So basically just try to understand those parts. Then how to draw it, we will see through the animation in the next slide. So first of all, here this particular is the alpha ferrite. So it has been started from that particular curve from 911, then it has been dropped up to the point P, that is up to the 7 to 3 degrees Celsius temperature, and again it will be revert to the 0 degree, okay, this particular curve. So whatever may be the present in this particular curve, that is the alpha ferrite, and below this the alpha plus Fe3C. Okay, so this will be alpha, this will be a alpha Fe3C. Now when we are adding the content of the carbon in it, so this will be a present the alpha ferrite plus perlite. So when we are adding the percentage of carbon, okay, so it will be a converting into the perlite. Perlite in the sense what? Okay, so that paramagnetic whatever may be the properties will be present over here when the alpha ferrite it is there. So we are knowing that when the iron will be in the pure form, so alpha ferrite kind of that structure it is there, and when it will be goes up to the 768 degree Celsius temperature. Okay, so in this particular zone, with some sort of that, when we are adding the percentage of carbon in it, okay, so might be it that will be becomes a paramagnetic at 768 degree Celsius temperature. Now this will be alpha ferrite. Whatever may be the term present over here, that will be the austenite, that is denoted by the gamma. And above this particular temperature of austenite, it will be delta ferrite. Here it has been shown, that is the delta ferrite. Now, when it is, these are the three main phases, okay, in this diagram, FAF3C diagram. So first you have to understood, this will be alpha ferrite at 7 to 7 or 7 to 3 degree Celsius temperature. When the temperature will be goes up to 1153 C, okay, that is degree Celsius 1153, and up to 1 here 1493, okay, so that will be austenite. So austenite will be trying to convert into delta ferrite in between those temperatures, so above 1400 degree up to 1538 degrees Celsius, the in between term, that is the delta ferrite. So these are the three terms. Okay, so in the last previous slide we have explained about this. Now when we are adding the percentage of carbon in it, here in this particular zone it will be alpha ferrite plus perlite plus cementite. So when again it is a eutectoid point for this, because everything will be solid. This is the eutectic point. This will be a eutectoid phase. Okay. So eutectoid point it is there. So what is the eutectoid point and all that we will explain in the next particular lecture. But here you just understand this will be alpha ferrite plus perlite plus cementite. When again we will go with this zone, this will be a hypo and this will be a hyper eutectoid. Okay, so this will be present, that alpha ferrite phase will be removed and only the perlite and cementite will be present. Then again from this particular point this will be a perlite plus ledeburite plus cementite, and finally it will be a ledeburite plus cementite. So in this way the phases will be there in this particular diagram. Initially ferrite plus cementite, then ferrite perlite plus cementite, Then ferrite will be removed, only perlite and cementite will be present. Then again, when we are increasing the percentage of carbon in it in this particular zone, then that will be becomes a perlite, ladeburite plus cementite. Finally, again that perlite will be gets removed and only ladeburite and Fe3C, that is the cementite, will be present. Similarly, in this particular zone, this particular common will be the ferrite plus austenite. This will be the ferrite plus austenite. This will be only austenite. Then this is austenite plus cementite. This is austenite ladeburite plus cementite. And again in this particular zone, that austenite will be gets removed, only the ladeburite and cementite. Okay. Now above this austenite, here everything will be in the liquid. So this particular common zone will be a liquid plus austenite. Here a small amount of, again the structure will be changes from BCC to FCC, again FCC, here will be a BCC. So this will be a delta ferrite. So this particular zone will be a liquid plus delta ferrite. This will be a austenite plus delta ferrite. So this term will be a delta ferrite. Delta ferrite, here will be delta ferrite plus austenite. Here will be a liquid plus delta ferrite. Now this particular zone will be liquid plus austenite, and here liquid plus cementite, and here everything will be in the liquid phase. So I think what are the different kind of that phases are there, you understood. Only we will just go with this next content, that is the alpha ferrite. So alpha ferrite, it an interstitial solid solution of carbon in low temperature. So we have seen here is the alpha ferrite. So alpha ferrite, it is just an interstitial solid solution which is present, okay, at in the very low temperature of BCC alpha ion. So it is almost a pure ion. So basically the alpha ferrite, that particularly will be a pure ion. So the solubility of carbon in alpha ion at a room temperature is 0.008% and increases with increasing temperature up to 0.025% at 7 to 7 degree or 7 to 3 degree. Now it is strongly ferromagnetic up to 768 degree Celsius and becomes a paramagnetic at 768 degree Celsius during heating. The temperature at which ferrite becomes a paramagnetic, it is called as a Curie temperature. So this will be, again we will see in the next slides. Now the next phase, that is the austenite. Basically it is the again the interstitial solid solution of carbon in FCC. So this will be the structure, austenite will be present in the FCC. Here that will be in the BCC. So it can be dissolved up to 2% of carbon. So here we can be able to see that in the austenite phase, the maximum 2% carbon, that is 2.06, means near about approximately 2% of carbon can be able to dissolve in it. Here maximum in the alpha, the maximum dissolve of carbon from 0.008% to 0.025%. So here we can be able to see 0.025. Okay, so it will be started from 0 to 0.025. Now austenite, it is the interstitial solid solution that we have seen. So the phase is stable only above the 7 to 7 degree, and it is soft, ductile, malleable and paramagnetic. So that we have seen. Now delta ferrite. So delta ferrite, it is an interstitial solid solution of carbon in high temperature BCC. It is similar to alpha ferrite. So again that structure will be changes into the BCC. Here just see in the alpha ferrite the structure will be in the BCC, again in the austenite the structure will be in the FCC, and again it will be changes the structure into the BCC again. So it is the interstitial solid solution of carbon in high temperature BCC, and it is very similar to the alpha ferrite because the structure will be same, that is the BCC, except its occurrence at high temperature. So only the occurrence will be gets changes at high temperature. So basically the alpha ferrite and delta ferrite are having or quite having the similar kind of that structure, that is the BCC structure, and only the austenite is having the different structure, that is FCC. So the last is the cementite phase. So here we have explained this will be alpha ferrite, this will be the austenite, this will be the delta ferrite, and here this will be a cementite. So cementite will be present, that is the Fe3C. So it is just an intermetallic compound of iron and carbon with fixed carbon contents up to 6.67% by weight. The cementite has a complex orthorhombic crystal structure with 12 ions and 4 carbon atoms. So with the 12 ions, iron atom and 4 carbon atoms in a unit cell, it is extremely hard and brittle in nature. So which is very hard. So up to the austenite phase, the structure, whatever may be the material will be there, it will be very soft. But in the cementite phase, up to 6.67%, it is a very hard and brittle in phase. So I think in the next lecture we will just go with this particular contents, that is how to draw the FAP3C diagram, and we will detail explain about the different phases. So I think the basic part of Fe3C diagram is clear to you now, and soon we will just complete the next lecture also, so you can be able to understand how to draw the Fe3C diagram and what are the detailed phases in it. So thank you very much.